Oh, now I seem to have lost part of my screen. Go. All right. We're not really keeping track of lecture numbers. And we'll see how today goes. We've got me, and I'm terrible with names. Nathan. All right. Yeah. So we just two of us live here today. The room is cool. I think there's been a move of some of the classes to other rooms. Uh, Assuming nobody has any real issues with where we are at the time, I'd rather not try to regroup into another room I mean, if we want, we can use it for the final exam. Actually, let me make sure that I am, yeah, all right. So I'm recording in live. Yeah, so we can move there for the final exam if necessary, but if the room is actually too warm for people to want to stay in, I would just say we keep it online. I can show up for those who want to do it, but I don't want to suffer through one of the Rathbone rooms in their projector. I kind of like this setup. So what we'll talk about today is least squares fitting. I've got the slides posted. It's the material consistent with what I had done in ME 400. So we're going to touch a little bit on what we had done in solving AX equal B for linear systems, right? Because least squares fitting, at least in the simplest case, ends up being a matrix-oriented problem, although there are some cases that go beyond that and require some of the nonlinear stuff, the optimization stuff that we've talked about. So I'm still working. Part of the reason why I seem like I'm running a little bit behind today is I'm still working on the project definition. I'm unearthing some old data. Basically, I'm trying to give as a rich problem that is a kernel for future use. That's something that I hope everyone gets good at in life is when making an effort, make sure that effort becomes a lever that you can use to do more later on with what you have. And so I am trying to do that. I uh, got the everything just working this morning. I ran something overnight, and I should be able to get that going. I think you'll have fun with it. I will try to make it a little bit more straightforward. In fact, this project, I think I will release it as a notebook oriented one. So the idea will be the following. You import a module that I produce for you. It'll be something that you install, I think is the way that I'll set it up, right? So we've used Anaconda, or many of us have used Anaconda. Is that what you have?
I use Jupyter.
Through Anaconda, or
Um,
did you just downloaded it by itself? So you have Python on your system,
yeah.
obviously. Yeah. So Python, but built in has something called pip, which is I think it's just the Python installer, Python something, but it's sort of built-in option for installing things. And so I've put together, this is what I mentioned last time. I've put together code that does have C++, so it's got to be compiled onto different systems. I'm hoping that I can set up the so-called wheels. It's so when you do pip install like NumPy, there's a file somewhere out on the web that says that is a wheel, and that has all the ingredients needed for pip to do its thing. It took some effort, but I have that for my own package. I just have to get that deployed. And we had Alex do a very quick sanity check on a Windows machine. So I'm hoping that will be fine. But I realized after that fact that the data that I had built in would have been it would have been too contrived. I want something that you'll remember when you get to reactor theory or fuel cycle or even senior design. And so I'll turn it into a notebook so it'll be much more guided than the other projects have been. I don't expect to do that in the future, but because we need to be a little bit flexible here. So any questions about that, let me know. And in fact, because I'm still working on that, I'm going to dash back home. I've got my work set up there. It's one of those things that if I try to transmit it here to the office, it's going to be 2 hours of momentum loss. So I'm going to go home after this lecture, which means that I'll take my laptop and have that on for office hours. So anybody who needs office hours during the normal time, just find me online. And many of you are in Reactor Lab as well, so share that with your friends. And I'm sorry because I think I noticed that for Reactor Lab this morning, the email that I sent saying that we didn't have lecture didn't actually leave the outbox until it was too late. So if I look like a hot mess today, it's not all my fault. Okay. Or maybe it is. Maybe I should just own everything. All right. So what I hope to do by the end of today is show you what it means to model data. That could be data that we get from an experiment or that we compute with some sort of simulation tool. But what we want to do is with a reasonably small set of independent variables, usually find how some response variable depends on the inputs. We want to capture that. And that sometimes it's straightforward to do, sometimes a little less straightforward to do. One of the simplest ways to model data is to assume that it is a straight line, a slope a times x plus b, with measured points through which this line should go. Right? And so you've probably dealt with this issue of scattered points on a graph, with the challenge being to draw a best fit line, right? And that's what least squares provides a solution to, right? So we'll use some built-in tools. We'll go through a little bit of theory, relating it back to the matrices that we've dealt with. So then we'll use that to do some built-in tool exploration. There are a number of things that can do linear least squares, and then we'll also look at things for nonlinear least squares. Did you by chance go to a different room before the? Okay, yeah, because there's been I guess it's gone all the way up to the provost that this room has been hot. So I got a mass email like Tuesday or something that all the classes in this room have been just reassigned randomly to other things, and it's like, given the work that we did to get into this room in the first place, I feel not offended, but just tired. So, we'll make do, right? And if I think with the number of people who've been going online, this will work out just fine. Okay. All right. So yeah, we'll use built-in tools for both linear least squares problems and nonlinear least squares. And of course, what it means to be linear versus nonlinear might not be very clear to you, but at the end of the day, know that if it's linear, there is a direct matrix solution. There's nothing nonlinear about it. And of course, if it's nonlinear, then we've got to resort to some of the tools, at least under the hood, that we've seen before with numerical differentiation, etc. Okay. So the familiar task that you all should have encountered, and if you haven't yet, you will for sure, is draw a line of best fit through some noisy data. Data or data. I switched between those two things. The alternative description would be find the A and B so that the linear model y of x equal ax plus b best matches the data. So what does this even mean? This one is an important, right? So we've got a model, linear model. Why do I call this a linear model? And a trick question. There are more than one answer for it. What's the first one that came to mind? This is yeah, it's saying that your output is a line, right? That depends on x. Okay. It's also a linear model in the statistical sense. And I'll describe what I mean by that. If we have an output variable, then we have two components of it that are added together. This one depends on x, but if you forget about that, really it's just a constant times something plus a constant times something else, and that something else here is 1. So b is the intercept, and in many models we'll have an intercept, because really what that does is it accounts for shifting a mean to the order. It doesn't always end up being the mean, although it can be very close to, depending on what the other things going on are. But this is a linear model because it is the equation for a line. But in a statistical or mathematical modeling sense, it's linear because it is a linear combination of these two things. Right? Now, when I say best matches the data, that means that there is something missing in this, right? And what we're going to find is that missing piece looks something like this, where that error term, epsilon, is going to be treated as though it comes from some sort of distribution. Now, if these were measured points, right, if we're measuring these in the laboratory, we're going to have some statistical error, some uncertainty. And we actually spend a bit of time early in the course understanding what probability distributions look like and how we can model that. So in a perfect world, that thing is zero against all the time. But in the imperfect world in which we live, the best that we can hope for is to find an epsilon or a model such that epsilon is on the average, not always necessarily zero equivalently, but something that on the average. So we're going to model that thing epsilon as a distribution. Now, we're not going to do that formally today, but in statistics, all the modeling stuff that we talked about today is primarily driving toward understanding what this thing is. Okay? What we care about today is primarily the coefficient, right? We want the best fit line. We're going to assume some things along the way about what the epsilon term is, but we're not going to try to quantify it. Right? Just know that if you want to learn more about what epsilon is, how to model it, then you can well, talk to me in office hours, or there are statistics classes, but that would take us too far out. I guess I will summarize in a final note saying that in the simplest case, in the best of all possible worlds, when we use this model, epsilon will end up being normal, a normal random variable with a constant variance, right? So where all of the errors for any individual measurement would be identically and independently distributed, something called IID. I don't know if I've mentioned that acronym earlier on in the course, but that's a common thing that we assume when we make measurements, is that each measurement is totally independent from the other one. So let's take a look at some of this data. Okay. So I've got some scattered points here that I generated randomly on the previous slide. And now I'm plotting them as a function of time, right? So I've got some time-dependent process. I'm looking to give myself a best line fit. And what I've done here for the two approximations is just use kind of eyeball. So I connected the first and last points, right? If I got scattered points and we think they like grow in time, I could take the first point, last point, use that to get my slope and get my intercept. So that's an easy thing to do, right? I could also connect what is it? That's the one thing. What is the other one that I'm showing here? Oh, the what is approximation to? Where did I where is my line? Ah, there we go. Okay, so connect minimum and so in this case, we're taking the first and last point of the data, but we can also find something kind of like a bounding estimate where we take the minimum point and the maximum. Now, in this case, it turns out that the lowest point of all the data is also the first point. So that's easy to do, and that's why both of those lines start at the same thing. Okay, but if I look at the maximum point, it's not quite the end point. So the slope of the blue line clearly is too large to capture the average behavior of everything. Okay, the red line is pretty good, but is it best? It kind of depends on what we mean by best. Was it best in the sense of it was easy for me to produce? Absolutely. Sometimes we have to account for human time in our definition for best. But if we're doing it strictly mathematically, we'll find that that is not necessarily the best. Okay. So what does best mean? Well, if we go back to that notion of having an error that I've now called an E with a subscript I, because for every measurement, there will be a unique error. I'm not going to get EI equals zero identity, right? It'll have some sort of distribution. We don't know what that is, but we are trying on the average to make that as small as possible and to have on the average in a value of U. So we have all these equations where we have an error is equal to the measured value y minus the model value y, or where we have, the model value y minus the measurement. So we have a model minus the measurement, and we have that for I equals 0, 1 through the number of points that we have. Okay. What kind of equation is this? Each one of these equations is what kind of equation? If I want to know, does that give me anything for A and B? Yeah, it's a linear equation. Now, each one of these is one equation And how many unknowns do I have? Two, right? I'm trying to find those parameters A and B. Okay. So over all of those possible measurements, okay, I can compute that error, right? For any value of A and B that I have, I can compute the error. Or if I have the error, well, if I have the error, then I have a problem solved, right? But if I know what if for a given value of A and B, then I can compute this quantity, which you might remember the double vertical bars. What's that? It's a norm, a vector norm in this case. We use it for normalization. That's why those words are related. So we take each element of the error vector, right? I've got a vector of errors now indexed by I square them, and then I add them up, and then I take the square root, right? That's the L2 norm, or the Euclidean norm that we've seen before, okay? So is this similar to the other error metrics that we've seen? Of course, because we studied several of them, right? What were the other two that were of interest? There's the Euclidean or L2 norm. Yeah, the L1 and the L infinity were the other options. So L1 adds up the absolute values of the elements, right? And then the L infinity picks out the largest absolute value of the elements. The L2 norm sits somewhere in the middle, right? If you think about what these errors, if we view this as an error and view it as penalizing something, what the L2, well, I guess we'll look at the boundary cases. The L1 norm, when used for errors, it tries to make all of the errors as uniform as possible, right? Because it's minimizing the way all of them contribute equally, right? With the L infinity norm, we'd be picking up just the last, the most offensive error, right? The biggest one. The L2 weights more heavily the larger error, right? So it tries to damp the larger error. So it might be that you don't get the lowest L1 norm, right? But it depends on what you want. In this case, the L2 norm is nice because anytime we deal with squares, we are working most likely with something that is convex, right? Because a parabola has that, if you take a parabola with its peak at the bottom, so it opens upward, then you have a clear shot to the minimum, right? So by choosing an error metric like the L2 norm, we automatically give ourselves in a set of equations. Well, we will end up with a set of equations that has a guaranteed solution. And that's wonderful, right? If we chose L1, not necessarily the case. If L infinity, also not necessarily the case, right? Anytime you have an L infinity norm and you're taking a max of a given array, that can make algorithms choke, right? Because then you get big jumps when you make changes, right? Because you could have one error that's the largest, and then you make some change, and another one becomes largest. It's really hard for numerical procedures to deal with things that are so discontinuous. Okay. So let's compute and plot the errors from the example and compute their L2 norms, right? So we've got E1 and E2, right? This should be, let's remember what the names of our approximations were. So we've got YA1 for the approximation 1, YA2, and then Y was the reference value. So the first error would be Y1, YA1 minus Y, and then YA2 minus Y. And then the norm of these, assuming we have NumPy loaded, we have NP linalg.norm of E1, and then NP linalg norm of E2. I believe, oh, Y, uh-oh, what did I not? There we go. All right. So if we look at these errors, one, our first approximation was better, right? If you remember, that was one where we took the first and the last ones. The second approximation is where we took the lowest of the points and the highest of the points and used that. They're similar, but obviously the first one is better. Both its norm is smaller and just visibly its errors seem to be hugging the x-axis a little bit better. Now, are they uniform? Is it the red curve? If I were to look at it in, maybe if I do this, I'll put it as markers instead, which is sometimes a little easier. And if I also put PLT plot T0, or T0 MP, 0, no, 0 times T. There we go. PLT. Okay. And then I'll make this. Okay. So ideally, we want our error to be here. If you look at the spread of the markers about that, the red dots, there are more of them below the axis than there are the blue ones. The blue ones are almost all on top. And that makes some sense because we chose the largest of the y values is our way to compute the slope. So we're overestimating. Okay. But if you think about it, we should see these red dots shift kind of on the average below, right? So we need to come up with a way to change this A and B so that those things will sort of on the average, when I add them up and divide by the number, give me 0. Right? We want those errors on the average to cancel out. So we can write this model in the following way. If you think about what we had a set of measured points, y, and a set of the independent variables, x. All of those individual measurements led to a single equation for 2 unknowns. If we take all of those equations and place it into matrix form like this, then we can end up with a unique solution for the least squares problem. And that unique solution is given here by this matrix equation. So this is the M is what we call the design or model matrix, okay? And we know the transpose, we take its inverse, and we have M transpose Y. The set of equations, or the equations that are listed here, these are sometimes called the normal equations. And it has to do with what the least squares approximation does to the error. Basically, the error that we get out will be normal to the solution. What does normal mean? 90 degrees orthogonal, right? So least squares is really a problem of orthogonality, right? Which of course can be defined in terms of vectors and so forth, right? So I'm just giving you this solution for the moment, right? We're going to explore it in due time. So how do we turn our previous problem into NumPy arrays that we can then use to find A and B? What would I need to do? I've already got my Y, I have my X. What can I do very quickly to solve this problem using the matrix syntax that we've seen before? And we'll go through a couple of ways to do this, but I want to do in the first shot, I want to do using sort of the basic ingredients that we've seen before. Now, first of all, can you see why this equation, right? So the equation that we have is this math bold x, math bold 1 times math bold, let's see, math bold C is equal to math bold. Okay. And then I need my extra. Okay. Can you see why this equation is not solvable in general? Remember, that's where this thing comes from, right? We've got MC, this is my M, so M times C is equal to Y, right? We would like to find the A and B, which I've tucked into this coefficient matrix vector C. So the first element of C is what? A, right? Because A goes with X, and then the B, the intercept, goes with the ones. That's just a vector of ones, okay? So in general, this will not be soluble. Why? We have n measurements. How many unknowns? 2. So if we have 3 measurements, that's a 3 by 2 matrix. 3 by 2 matrices, do they have inverses? No, the only thing that could possibly be inverted is a square matrix. And if we have lots of measured points, we can't invert that matrix, right? So that's one of the reasons that we have to do something different. Because we have a set of equations that is, in this case, significantly over-determined, right? The matrix is tall and skinny, so it has no inverse, and that means we have too many equations for too few unknowns, right? So let's set up these arrays and matrices and see if we can find the best fit parameters A and B. So the very first thing that I want to do is make that matrix M. So I will do it as NP array. Actually, yeah. Let's take a look at it like this. So I take NP array. The first element of this array will be the X array, right? So X is a vector. And then I need to make a vector of ones. Anybody remember how to make a vector of ones? Lots of ways that we could do it. You just need to remember one. How about np.ones? Right? We could do np.ones, and then I don't know if we save the length of n. That would be a way to do it if we had n ready to go. An even easier way, because it's my job to teach you the path of least resistance, is x to the 0 power. Yeah, that's my favorite way of making a ones, if I already have something. So if I make this matrix M, we can take a look at what it is. Oh, it was T, wasn't it? My bad. We're dealing with T, not X. Okay. What's the problem with this matrix? Does that look like N by 2? No, it looks like it has 2 rows that are really long. So I've made the transpose of that. So one thing I can very quickly do is take the transpose here, and now I've got my column matrix, okay? That's one way to do it. The other way that we can do it is to do NP column stack, and then we get the same thing. Whichever one you want to use is totally fine, but you saw what I did, and my method was this. I make it, I look at it, and I fix it. Right? So use that sort of cycle. Always be, anytime you're constructing something like this design matrix or model matrix, do some visual inspection. Make sure you know what you've got before you go on, because if you did what I originally did without putting the transpose, you'd get to the rest of it and you would have dimensional issues, errors, and it might take you just a bit longer to figure it out. Okay, so be diligent as you go along. So we've got the M. That looks good. And then we need to define this system. So if I'm telling you here that C is the solution, okay, what is the linear system that is actually being solved? We see a linear system. So by inspection, what is the matrix equation that is ultimately being solved? What is the matrix that's being inverted? Yeah, M transpose M, right? That's key. So I can make this matrix M, I'll call it MTM for M transpose M, and that looks like this. That works. Okay. Now, if I take that M transpose M and I move it over to the left-hand side, okay, what does that leave on the right-hand side? M transpose Y, right? So I can do M transpose Y. Okay. Now, what do you think the size of M transpose M is going to be? If it's N by 2, and we take its transpose, that's 2 by n. So if it's M transpose times n, that's 2 by n by n by 2, which results in 2 by 2. Aha! You can see where the magic of being able to solve it comes from. It's that M transpose n. That gets rid of the dimension n. Okay, we don't know why this works yet, but it does work. Okay, so if I do MTM and I look at its shape, it's 2 by 2, exactly as needed. And if I look at my M transpose Y and its shape, it's, so I should put my Y there, it's 2, right? So we have two equations, two unknowns, and we can solve it directly now. Anybody remember what the magic command is? 2 by 2, so you could definitely do by hand, but I don't want to do this. But we could actually look at the elements. That's probably not a bad idea to look at these elements. If I look at M transpose M, yeah, there's some numbers there. I could invert this matrix. I could take a look at the right-hand side. I know I could solve it, right? We could get the values of C, but we don't need to do that. We've learned the trick to do that, and the trick is np.linalg.solve, right? Which implements the elimination algorithm that we've seen before. So the coefficients that I care about are C. They are the solution to np.linalg.solve M transpose M with a right-hand side of M transpose Y. And if I look at those elements of C, I will find that I have a slope of about 5.5 and then an intercept of minus 2.23. Okay. I don't know if those look good for what we have before, but why don't we take a try? Now, before I move on, though, this C, my solution, is not exactly what I was looking for. I'm looking for A and B. So how do I get A and B from C? Again, more than one way to do it. The syntax that I like is unpacking. What does that look like? A comma B is equal to C, right? And so I'm actually going to put A opt and then, or actually A, let's say ALS and then ALS for least squares. Okay. Now it's unsatisfying unless we see it in action. So what I'm going to do is give myself another box here. And then I'm going to take my plots from up here. And then I'm going to take my, oh no, we've run into another conundrum. If I want to compute my error for the third approximation, my least squares approximation, I need my least squares approximation for y. But all I have are the coefficients. So what do I do? I have the coefficients C, the ALS, and the BLS. How do I get the y's? In fact, I can put that here. I've got the YLS. What should that be? Yeah, I could just plug in. I could say ALS times C plus BLS, right? That would be totally fine. And that's maybe what you would do in practice if you did it by hand. Another thing that you can do is use the original design matrix and the coefficient vector. So I could do either of these. That works, but also that works, right? These are identical. That's the power of the design matrix, right? Because what we're going to see is that even within the context of this linear least squares process, setting up A trans or N transpose M and so forth, it doesn't require us to have such a small model. We're not limited to just T, right? Would anything mechanically have changed if it were A times T squared plus B? No, you would have just had T squared in that matrix instead of the T. Where you would have a T squared without the T, I don't know, but it could be done. In fact, you don't even need the T squared, or you could be a sine of T. There could be anything. And you put anything you want in those columns of the design matrix, all these equations work out the same. So in this specialized case, this highlighted ALS plus T plus BLS works. But for the more general case, this is how you get that approximate solution. So I will say E3 is equal to YLS minus Y. I will take the norm, E3, and then I will plot the E3, and then I will make this a, oh, maybe I'll make this a green star. And then add one more of these things. E3, E3, I think. Oh, E3, where'd my... Aha. So now if we look at what we get in the errors, we can see a pretty major improvement, right? Our L2 norm has gone below what our original one of 30 was, right, down to 25. And if I eyeball those green stars, they are reasonably split half and half above and below the x-axis. So this is an indication that we've done the right thing. Okay. Could we prove that it is the lowest value? We could definitely do some quick number crunching, maybe do some perturbations. What would be an easy way to demonstrate that this is an optimum? At least a local optimum. I can tell you it's the global optimum because of the math, but how would we numerically verify that this is indeed? Where do extrema live? Extrema live where something goes to zero. Yeah. So in this case, this least squares problem, if you think about what we've done, we've minimized this thing. Okay. I didn't formally state it, right? But the solution that we get when writing this set of equations is actually the solution to the minimization problem where find C such that the norm, L2 norm of E is minimum. So it is an unconstrained optimization. So we could take this expression, the L2 norm of E, which can be written in terms of A and B, the elements of C. And then what do we do with it? We take its derivative, set it to zero. And would you believe it? These are the equations that pop out of that system. Okay, so you'll get to see that a little bit more in the reading. So go and do the reading online for this. But the basic idea is if we start off with the definition for error, okay, I'll put in one more little block here. If we start off with the definition for the error, right? So we've got f of A and B is equal to the L2 norm of the error, right? That's what we're trying to minimize. And so what we need, and we could call this equivalently f of C, right? Where C has the A and B, right? And so then we need, right arrow, we need this to be zero, right? We need the gradient of our objective function to be zero. And that, when you take the expression for error, which in terms of the matrices is the following, right? This is equal to the norm of the design matrix times C minus the measured values Y. Okay. But that, because it's the L2 norm, that's actually equal to this expression here, transpose with itself. Where is transpose? Okay. So this thing here, sorry, I have to put the square root. Okay. So we have the matrix, so the objective function is f of AB, which is equivalently f of C, which equivalently is the L2 norm of the error, which is equivalently the L2 norm of the design matrix times C minus Y, which is equivalently the square root of MC minus Y transpose with itself. And when we take that thing, take its partial derivatives with respect to both A and B, we end up with two equations or two unknowns. And that is what the normal equation does. That's what the linear least squares solution does. It all comes from that little bit of magic from earlier, that the extrema of the problem show up where the derivative of the objective goes to zero. Any questions about that? One other thing that I will show you is that we can solve this using one other approach. me go here. Okay. So there is one other way that we can do it. YLS2, I'll say, is inside of NumPy, there's an additional solver specifically for solving least squares problem. We know that the only thing that you need to solve to set up the least squares problem is to take M transpose M, and then M transpose what your original right-hand side was, okay? So the only information you really need is M and Y, and you can take the transpose. So NumPy has a built-in least squares solver that does that automatically for us. And so if I do M and Y, and that should not be YLS, that should be C2. We will see what it produces. And it looks like it produces the same things, although it gives us, as some packages do, some additional information, right? So if we take a look at np.linalg.least_square and its documentation, we can see that it returns the solution that we care about, the residuals, which would be equivalent to those errors that we reconstructed and plotted, the rank of the matrix A, which will tell you something about the number of independent columns, right? Which for our case, if we're giving it this A, what do you think that rank is? How many columns do we have? Yeah, two. So as long as those are, we're in big trouble if in those two columns, we only have one independent column. So if you gave it a column of ones and a column of twos, then least squares is going to argue, because even after you do the A transpose M transpose M, you end up with a 2x2 matrix that itself is not invertible, right? So you've got to have at least two independent columns for two unknowns. Okay. All right. So beyond linear models, not all data is intrinsically linear. Some alternatives that we can have are polynomial models, where we just add up different powers of n. But we could also have problem-specific models where we know there's some functional form with respect to the independent variables. We could add up all these exponentials if we want. I mean, it's fine with cosines. But the key here is that the coefficients are weights, right? We are finding this linear combination of what is sometimes called basis functions. Basis functions are used to evaluate the columns of the design or model matrix, right? But that's the key idea. As long as you are adding up terms, then you can use the linear least squares method to find the unique solution. Some other tools that help us do that would be like polyfit and polyval, right? So we can use polyfit and polyval to approximate something like sine. We could use it for the previous problem too, but let's suppose I have a function y. It's just the square of the sine, and we want to evaluate this for x equals 0 to 2. Okay, so if I want to approximate this as a line, just like we did, or as a quadratic, or as a cubic, could totally use the design matrix approach that we just did with regular least squares using np-linalg solve or in np.linalg least squares. But the other thing that we can do specifically when we have polynomials is polyfit and polyval. And so what I can do here is say P is equal to NP polyfit, give it the X and the Y. And then if I take a look at what degree equal 1, so P1 would be my my values, okay? Now, it's not necessarily clear which coefficient is which. I know for a linear ax plus b, I have 2. I don't remember how polyfit returns those coefficients. So what could I do? What's that? You read the documentation, exactly. So np dot polyfit, and you give it x, you give it the y's, you give it the degrees, some other things if you want them, and then it returns p, which gives us the highest power first, which means the first element should be equal to the slope, right? Or the quadratic or the cubic term, depending on which power we're doing. So what we can do here is compute the polynomial coefficients for both the quadratic Okay. It'll do the same thing. Now, we know what the coefficients are, so we could reconstruct the solution ourselves, just using those 3 or 2 elements of the P. But there's also this nice function called polyval, which lets us evaluate the polynomial at any new value of x or even the old ones, right? So if I do polyval, what it'll take in is the parameters P that we just computed, and then the x values at which we want to evaluate the new polynomial. So if we want to do y1, that would be NP polyval P1 x, and then copy and paste. And then we can make a plot of all of it, x, y, y1, x, y2, x, y3. And you can see what these different approximations look like. Okay. Which one is the true one? You don't know because I haven't made a good plot. I didn't put my labels and so forth. But I do know NumPy and Matplotlib well enough to know that the default color is blue. That's the first one. That is the raw or the raw sine squared down. Right? So we have blue, and we go to orange for the linear. We go to green for the quadratic, and finally the red is cubic. And visually, that's pretty good. Okay. It would fail horrendously if we extended it past this domain, right? Because the sine itself is, well, oscillating forever, whereas the polynomials will blow up eventually. And I guess I did it already. Good. All right, so beyond polynomial models and some of these other things that are simple additive models, right? That in statistics, they are all known as linear models because they are linear combinations of these independent regression variables or the columns of the design matrix, right? Could be functions of some other independent parameter, but that's what's done there. So here we have a different kind of model, right? So if we have a measured quantity y that we think is sinusoidal in time, right? Now we've got time inside the sine, but we also have some parameters inside the sine. It's a times sine, but there's also some unknowns that live inside the function. That makes this nonlinear, right? This is not simply a times something plus b times something plus c times something. Those b and c live inside of the nonlinear function sine. Okay, so in this case, we've got to use something a little bit different, right? In the end, it is still a least squares process. And really, it lives on top of the optimization we've done because we can still take a model, some measured data, compute an error, compute its L2 norm, take its derivative, and set that to 0 and solve. The problem is that derivative itself depends on those parameters. So if we take that derivative and we solve and we make a new step and we find the next best thing, it could be the case that the next thing actually takes us in the wrong direction, right? Hopefully we keep going downhill. But we could use all that. Now, in SciPy.optimize, there's a nice tool called CurveFit that sort of it puts all of it together in a way that makes it so you don't have to individually call things like optimize or fsolve or anything like that. It just puts it all together using the sorts of tools that we've seen so far, right? So we've got some data here. This would be the powers for a reactor on a positive period. So that's if we went over to Ward Hall and operated our reactor, maybe the reactor operator has taken out a control element a little bit so that we can go up in power, normal operation. Okay. So what I'd like to do is find out what the power is as a function of time. And if you look, this is a times an exponential times b times t. So it looks deceptively simple, but because that b is inside the exponential, this is not a linear problem. This is not something where we can break it apart as the sum of independent vectors. Okay. Now, before we do move on to the curve fit solution, do you think there's a way that we could use the linear regression that we did before, right? This process of finding a best straight line through the data, or in other words, just something where we could turn it into something that we could use the least squares process that we've just seen, or polyfit or whatever. Is there anything obvious? Exponentials are definitely nonlinear, but what's a great way to remove an exponential? Yeah, take the log. What happens if I take the log of both sides? I get a log power, which maybe that's a meaningful quantity, maybe not, but in any case, it gives me something. Okay? So if I take the log of p, that's its own thing. What happens when I take the log of a times e to the bt? If I take a log of a product, that's equivalent to the sum of the logs, right? So a times e to the bt, if I take that log, that's log a plus log of e bt, the bt, moving down. So I've got then log b, which goes away. So I have log a plus bt. So now I have log p is equal to log a plus bt. Well, isn't that just another y equal ax plus b with some switched notation? Yeah. And that's called a transform. That's a powerful fuel. So if you have data that follows an exponential or other power law, logarithms can be used to transform it into something where other methods can be used. Now, in practice, that might be totally fine. There is a statistical basis for it, right? There are some transformations that still land you in a place where, after all the fitting, you can make statistical inferences. But for here, it's just kind of convenience. If you had nothing else, you could take the log and turn it into a problem that you could solve using what we've seen already. Okay, but if we want to be able to use this with the data given here and solve for that particular model, then we want to actually do this. Now, I suspect I had the data in maybe a separate Python file, but what I'm going to do here is quickly turn this into two arrays. And here's what I'm going to do. I'm going to say ChatGPT, and then please make two NumPy arrays. Yeah, you can see I have some issues. I have an electronic drum set and my snare trigger is gone. So all I can do is rim shot. That's really not fun. See, this is a perfect example of in the syllabus where I say if it's busy work, have GPT do it. We all know how to copy and paste and type. And so we'll just do it like this, right? So now I will call this T and this is P. And then we will plot T versus P just to make sure that we've got what we need. That looks good. Maybe make it some O's so that, because it's better to show markers for measured data. Okay. So that's what we need here. Now to make the fit from SciPy dot optimize import curve fit. Okay, and I'll make this a fragment and then take a look at what curve fit needs. You're going to see a familiar pattern for elements that seem familiar. Curve fit will take f. F is our model. That's going to be a function that when given the independent variable x, or t in this case, and then separate arguments for a and b, the constants that we care about, it will return the measured value or the model value. Okay. So in order to make the fit, though, we need the reference depth. So we'll give it the times and we'll give it powers. If we have an initial guess for those parameters, we can give it, although it will do without. In my experience, well, the suggestion I have given a couple times now is initial guesses are important. So is it as important for curve fit? I feel like curve fit has some bells and whistles that help soften the issues, but still, if you had a reasonable idea what it could be, use that. Where could you get a very easy first guess that you know is probably pretty good? Take the log of both sides and to find that solution, right? Because that should give you that gives you a best fit under some transformation, right? So maybe it's not the best fit in like weighted with powers, but it's best in some right? And you could use that as a first guess. Okay. There are some things related to what we assume about uncertainties, right? Should the errors at larger times be weighted differently? And you can imagine that if this were based on counting statistics, who's had 612? Taking it right now. What is the fundamental rule about uncertainty with respect to counting? I should think of sure, you need total counts, right? And what is the uncertainty of n if you count? Square root of n, right? So it makes sense that if our power is proportional to the number of counts, then the uncertainty in power grows. Not necessarily the relative uncertainty, but the actual uncertainty. And so we might choose to weight those deviations with a larger, and that's where that sort of stuff comes in. Again, that takes us kind of outside of our scope. Just be aware that you can weight your errors, okay? And you'll see that a little bit more in reactor lab. Now that we're pushing some of this material here, we'll be able to expand on that. And there's some other things like if you know what the Jacobian is, we can do that. But we really just need the first three arguments, and then maybe the fourth is our initial guess. So if I take my curve fit, I will give it my model, which I haven't actually made yet. I will give it my measured times, my measured powers, and then P0 will be my initial guess for the parameters. So in order to define the function, right, I should probably do that. We'll look at the documentation one more time, right? It tells us what that function should look like. So it's a callable function that takes as its first argument the x, that's the unknown, and then the parameters in order. So if I define that, def f takes in t as its as the parameter, and then we have an a and a b for our exponential. And then all we need to do is return a times np dot x of b times t, right? That is our model for whatever a and b we happen to have, okay? So now we give that model to CurveFit. We give it the raw data t and p that we have. And then for an initial guess, I mean, what would be why don't we try it without and see if it gives us something that even makes a little bit of sense, right? I'm going to take a wild leap of faith and think it returns more than just my solution. So I'll just call that whole thing a solution, and then I'll print it out. And what you see is it actually returns two things. One, the two elements, and that you can identify rightly as the A and B, the order they show up in your model. The second one is the covariance matrix. So the covariance matrix tells us something about how the value of A and B relate to each other or correlate with each other with this fit. Now, if we were to take the solution and then plot the results. So let me copy my plot up here. So if I take this and now I say I have my P approximate, okay, I can take the solution, its first element, that's my A and B, and I could just do A times whatever, but I can use my model. I already have the model. So if I take F, I can give it T, and then I could do sol 0, but sol 0 gives me this, okay? I could do sol 0, 0 for A, and then I could do sol 0, 1 for B, and I could maybe even break them up out here. But I can show you something else too. Whenever you have a function that has a list of unnamed variables, right? These are what's the name for it? Just args, right? So if you have a list of just unnamed arguments and you want to pass them all in at once, you can do it using a sequence. That could be a couple or a list, probably even a NumPy array. I hope here. What do I mean by that? So rather than using this whole highlighted business, I could take sol 0 and effectively unpack it in place by putting a star. This is one of those extra details that lives somewhere in Miami 400 notes on functions, right? So it's there. Let's see if that works. It does rotten. So now let's see if we get what we want for the approximation. I'll make this a green dashed line. And I feel like I've earned my degree, right? Because that fits pretty darn well. Obviously, it does not capture all the movement. So if we were to look at the errors, we would have some spread. Now, I said something about that covariance. What that covariance says is of the wow, I don't know if that is quite right. Just based on the errors that were made, you can say something about the uncertainty in those parameters A and B. Right? We didn't say anything about that with the least squares approximation, but there is a way to estimate the uncertainties. Because if you think about it, if the measurements that we make are themselves random, if we are treating this as a random experiment as opposed to just fitting numbers to other numbers, then those measurements are uncertain, right? And they're random variables. And so with all these calculations that we're doing, we're ultimately defining A and B in terms of a whole bunch of random variables. Well, what is a function of random variables? Is it itself a random variable? If I take two random variables and I add them together, that result is random, right? If I take two random variables and I multiply them together, that's also random. So all of these parameters that we get out of the fitting process are random if we assume the data that we put in was also random. And so then things like the covariance start to have a meaning. We'll get to know what those are later on. But this gives us the line that we're after. Okay. So I'm hoping now you know what it means for a least squares fit, what it means to find a least squares fit to some scattered points, right? Using just a simple linear model or some other model that are just additive. Okay? But when we get into things that are not additive, we've got to use some of the nonlinear techniques, many of which are bundled up kind of behind the scenes in that curve fit. So trying to think if there's anything else. So we got about 7 minutes left. I think this covers everything that I would want to about the least squares. I do encourage you to look at the online things to go through. I think in the notes I actually showed using calculus how the least squares equations, how setting up that tall skinny matrix leads to the least squares solution by way of the normal equation. Right? And we could connect that back to linear algebra. There you can do it all through linear algebra and orthogonality too. But any questions about this? Any questions from online folks? Assuming they're still there. I see a thumbs up. So I will call it a day. Remember, I will be on office hours on Zoom from 11:30 to 1:30. If I walk away, just stick around and maybe send a message or something. Actually, and is anybody planning to pop in on Zoom today? Anybody online planning to? Give me a thumbs up if you will. Do nothing if you won't. And nobody wants to see me. That's fine. I'll get my work done then. All right. I'll be there anyway. Okay. I will see you all on Tuesday.